Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper machine learning. In this and to the next module, we will be talking about a topic called support vector machines. So, let us first start with the first module on support vector machines. This has been developed by this team of people who are responsible for creating this module. Now, let us look at the learning objectives of this particular module. That is the first module on support vector machines. Now, support vector machines is a particular machine learning technique that has been used extensively for all type of application, especially classification applications. So, here we are trying to understand the principles of linear and nonlinear support vector machines, or SVM as they are called. Then we want to know the interpretation of what is called as kernel functions. We will come to that. This kernel functions has become very important today in other techniques also, other machine learning techniques also, but it initially started with SVM. And to acquire knowledge about solving the optimization problem that we need to solve in a support vector machine, we will come to that and explain what is to be optimized. And these are the keywords: margin, slack variable, kernel trick, and hyperplane. Okay. So, let us look at the introduction. This particular support vector machines, or SVM, were proposed by Boser, Guyon and Vapnik in 1992, and today it is gaining increasing popularity, especially recently. Most of the baseline methods start with support vector machines. Basically, it is an algorithm for learning linear classifiers. That is how it started off in 1992. And it is motivated by the idea of maximizing the margin, and this is a new concept at that point of time, because up to then classifier did not use this principle or idea, and it is an efficient from non-linear we go to an efficient extension of non-linear through the use of something called kernels. We will come to these concepts. So, there are one or two basic concepts that are new. One is this maximizing the margin, and the second one is handling non-linearity through a use of kernel functions. Now, first let us look at what is a linear separator. Now, this concept is something that we have studied in 2 dimension when we were in school. Y is equal to mx plus c. So, this is a basic concept that we studied, where we have a line in 2 dimension. A line is represented by that concept of y is equal to mx plus c, and basically that line separates now we can look at that line separates 2 different objects into 2 classes, binary. So, binary classification can be viewed as a task of separating classes in feature space. Now, if it is 2 dimensional feature space, it is very trivial. We are talking about an n dimensional feature space. That is why we talk about the task of separating classification as separating the classes in a feature space, and there you have a plane. If it is 2 dimensional, you have a line, you have a plane separating the feature space into 2, one belong to one class and the other belong to other class, depending upon the sign. Function of x is a sign. We will go a little more detail into this. So, you have a function that you give a input x to a function, and the function will decide, you have 3 parameters there, w, b and x, and w x plus b. Please note that it is not a simple linear line, but here for understanding sake we have represented it as a linear line. So, depending upon whether it is minus w x plus b or plus w x plus b, your data gets classified as either positive or negative. Here we have the dark circles representing +1 and the transparent circles representing -1. So, you classify this data like this. Now, the question is, you have a line, how do you magically find this line? Okay. So, that is the idea. So, now you have another dot, and this will be misclassified sometimes as plus. Okay. So, can we draw the line differently? Okay, can we draw the line differently? That is the next question that we have to ask. Now, so which of this separator, why is it called a linear separator? It is a separation that is represented by a linear line, but a linear plane, a linear hyperplane, depending upon the number of dimensions you have. So, which of these linear separators is the optimal separator between the 2 classes? That is the crux of support vector machine. So, here you have two classes red and blue, and you can see that there are so many lines you can use to separate these two classes. Okay. We always represent it by using linear 2 dimension, plus please note this is can be any m dimension. Okay. Now, let us look at this classification margin, which is the crux of the support vector machine. So, the distance from an example xi to the separator is r, let us assume. Example closest to this hyperplane are what are called as support vectors. Why are they called vectors? Because they are not a point, it could be any number of depending on the dimension. Okay. So, margin rho of the separator is the distance between the support vectors. These are the three different things you should understand when we talk about support vector machine. What is it? You have an example xi, okay, distance from this example to the separator. Remember, the separator is that plane or line. Okay. So, that is r, let us assume. The examples which are far away from this hyperplane, the separator, is not very important. The ones that are closest to the hyperplane are called as support vectors. Okay. And there is a margin that separates the two, the distance between the support vectors, that we will call as rho. So, if you represent it by a diagram, here you have r is the distance between the example and the plane. Okay. Then you have here rho is the margin that separates the two vectors. Now, if you look here, we are bothered about the red circled and the blue circled because they are the support vectors which are nearest to the hyperplane. And now you see rho is the distance or the between the support vector. So, you have a red support vector and the blue support vector. So, the distance between that is rho, that is called the margin. Okay. So, now you have a plane, you have a distance of any example from the hyperplane, and then you have the ones closest which are called as the examples which are closest to this hyperplane where the distance is the least, that is called as support vectors, and the margin is nothing but the distance between the support vectors. Okay. So, this r, which is the distance, can be written as wtxi plus b. Remember that hyperplane is wt plus divided by the w, that is the weight of that. So, this is the r, the distance between the plane and the example. Now, if you take the classification margin a little more in detail, now this is the margin. So, you define the margin of a linear classifier as the width that the boundary could be increased by before hitting a data point. Now, we are just changing the definition of margin. There we said the margin is the distance between this support vectors. Now, what we are going to do is we are trying to define the margin as the width rho. Remember the width rho, that you could keep on increasing this rho till you hit data points. Remember, the data points are support vectors on either side. So, you keep increasing that, that is how we define margin. Now, the maximum margin linear classifier is the linear classifier with the maximum margin. How much ever you can increase, you try to increase it. So, this is the simplest kind of SVM which we just called as linear SVM or LSVM, and these are the support vectors that the margin pushes up against. So, when you keep increasing the margin, it will push up against data points on either side, the positive and negative. We are talking only about binary classification. So, those are called as support vectors which you have already defined previously. So, again to repeat, maximizing the margin. So, our job is you keep increasing the margin till it touches the data point. So, maximizing the margin is good both according to intuition and according to the pack theory. Okay. Probably approximate theory, that is called, implies that only support vectors are important. Now, what is the importance of this? We are not bothered about all the data points that lie all across the feature space. We are only bothered about those data points that push against the margin or the so called support vectors. Other training examples are almost ignorable, and empirically this works very, very well. Okay. So, this is the crux and the important concept of the support vector machines. So, mathematically if you talk about linear SVMs, we will come to nonlinear later. Linear SVMs, you have x plus and you have the red one and the purple one, and you have wx plus b equal to 1, wx plus b equal to 0 is the line that separates, and wx plus b minus 1 comes on the other side. One is the positive class, other is negative class. So, this is the margin width, and this is the how you define the margin. The margin is defined as x plus, that is the samples on the positive side, minus x minus, the margin is on the negative sides, into w divided by the w is equal to 2w. So, you will get this as 2w, 2 by w, this is called the margin. Now, can we represent this linear SVM mathematically? Yes. So, let us assume the training sets are xi to yi, there are n such points, and this sits the x sits in a real space dimensionality, and yi has only two values, minus 1 and plus 1, that is it is either positive or negative. So, that is what we have. Now, this is separated by a hyperplane with margin rho. For each training example xi yi, wt xi plus b is lesser than or equal to minus rho by 2 if it is on the positive side, I am sorry, if it is on the negative side, and it is greater than rho by 2 if it is on the positive side. So, you can say that yi wt xi plus b is greater than or equal to rho by 2. So, that is how you talk about this. So, depending on that you will get it as minus 1 or plus 1. For every support vector xs, the above inequality becomes an equality. Okay. So, after rescaling w and b by rho by 2, we obtain the distance between each support vector and the hyperplane as r is equal to yi. We have replaced that yi is equal to wt xi plus b divided by the modulus of w, that is equal to 1 by w. So, the distance between each support vector and the hyperplane is 1 by w. Okay. So, this is what we have, how we represent the linear SVM mathematically. Basically, but what we are saying is, we are looking at points on the support vector points, but that is why we have this distance as rho margin. So, support vector points or support vectors on one side of the line as positive, the other side of the line as negative, and we are looking at what the distance between each support vector and the hyperplane will be, that will be 1 by w. Okay. This margin, the margin can be expressed after rescaling w and b as rho is equal to 2r, that is initially we had rho as some other value, now we have 2r, that is equal to 2 by w, that is the rho or the margin. Okay. R is the distance between the support vector and the hyperplane, and the margin size is equal to rho. Now, we can now remember what we wanted to find. We wanted to find a plane that that optimizes this distance or the margin. So, we can formulate this as a quadratic optimization problem. So, find w and b such that rho, that is the distance or the margin size, is maximized for all data values which lie between 1 and n. So, what we want to find is, we want to find this equation y, the value of y such that wt xi plus b is greater than or equal to 1. So, we want to maximize the w and b. In other words, we want to find the slope and the distance from that y is equal to mx plus c. Finding m and c, or in our terminology w and b, is the main job of SVM. That is, we are finding the best plane which maximizes the margin, okay, which can be reformulated as find the w and b such that this particular phi w or the w squared is equal to wtw is minimized. So, what do we want is, we want that to be minimized such that for all values of x and I data points, this is true. So, we do not know which is the support vector, we do not know that, but we want to find a plane, because depending on the plane's angle, the support vectors change. So, we want to find such an xi and yi, for all xi and yi, we want to find the w and b such that this rho or the margin is maximized. Okay. Now, we want to solve this optimization problem. So, we want to find a w and b such that phi w is equal to w to the power of t w, which is to be minimized, that is to be minimized for all values of x and I, where yi of wt xi plus b is greater than or equal to 1. So, you need to optimize the quadratic function subject to linear constraints. The solution actually involves a dual problem, where a Lagrange multiplier alpha is associated with every inequality constraint in the primal problem. We looked at one alpha when we were just talking about the classifier. I just ignored it at that point of time and just told it as a line. So, this alpha comes into the picture, which is a Lagrange multiplier. The job is to do the inequality constraint, to take care of the inequality constraint. So, for find the alpha 1 to alpha n such that this alpha is equal to sigma alpha I minus this equation, which is to be maximized. We want to find the maximum value such that this is maximized for all values of alpha. I mean, we want to find a value alpha I such that the summation becomes equal to 0. So, that is what we were talking about as the optimization problem. So, basically we are using the Lagrange multiplier as a mathematical technique to maximize this row and find the value of W and B. Okay. So, that is reworded in the terms of Lagrange multiplier, and this is the equation you get. Now, we go to the soft margin classification. What is the soft margin classification? So, what if the training set is not linearly separable? Here we made a very convenient assumption till now that I can separate the data points rightly using a line, whether it is a n dimensional line or a single line, or I mean 2 dimensional, 3 dimensional, n dimensional. It is linearly separable, that is these data points and this data points, there is a line that you can define or a plane that you can define. So, that is linearly separable, that is what we assumed, but it is not necessary. So, you have something called slack variables eta that can be added to allow misclassification of difficult or noisy samples, resulting in a margin becoming soft. Okay. So, what we are trying to say is, if you have data points, okay, that are not linearly separable, then you introduce something called a slack variable. Do not make it very strict, that is the meaning of slack eta, which can be added so that you can allow some sort of misclassification of difficult or noisy samples, which will result in the margin not being strictly linear, it will become a little soft, not little soft, it is called soft. So, if you look here, you have these data points. So, now look at that red data point on below the line, that is a misclassified example, or the blue above the line, again it is misclassified. So, now you are introducing that eta, which is the slack variable, to take care of this. Okay. So, how do we define it mathematically? So, the old formation as we saw is this, the original formation without the Lagrange multiplier, where we wanted W and B such that the the margin is minimized, I am sorry, such that the row is increased and the distance is thick. So, the modified formulation incorporates slack variables. So, find W and B such that phi of W is W power of T W plus, now we are introducing something called C eta I. We will talk about the C again in the next module, but of now we want this particular aspect to be minimized, and for all xi and yi which belong to where I is 1 to n, we want this to be greater than 1 minus eta I, that is before we had greater than or equal to 1. Now, we are introducing a term called minus eta I, where eta I is greater than or equal to 0. So, the parameter C can be viewed as a way of to control overfitting. Remember the concept of overfitting that we were speaking about, that is what is overfitting in general, where whatever model you are having exactly fits the data points. Okay. So, if you have a large slack variable, it means that you are modifying the margin to fit exactly into the data available to you, which is overfitting. What is a negative of overfitting? That if you bring in new data points, it may not do the work correctly, your prediction will not be good. For all samples it will be very good, that is the overfitting problem. So, by increasing the role of plus C eta I, by increasing the role of eta I, you are going towards overfitting. Okay. So, what is the solution? It is again a dual problem, it is identical to the separable case, linear separable case, where we would need an additional Lagrange multiplier to take care of the slack variables. So, you find an alpha I and alpha n such that you have the same thing that we did last time, except that additionally we have to take care of the Lagrange, I mean the slack variables. Again xi with non-zero alpha I will be support vectors. So, you have this particular problem where yk is equal to 1 minus eta k, and eta k is that slack variable. Again we do not need to compute W explicitly, because for classification we do not need to do that, we just need to find the value, the plane. So, f of x is equal to summation of alpha I yi xti xi to the power of t plus b. So, we are not calculating that specifically. Now, what is the theoretical justification for these maximum margins? That is the next question we have to answer. So, Wapnick, this is the person who discovered the, as we said, the support vector machines in 1992, one of the authors. So, he said that the class of optimal linear separators has WC, that is, which is called as Wapnick-Chervonikis dimension H, bounded as the following. H is less than or equal to minimum of d squared by rho squared to the and m naught plus 1, where rho is the margin, d is the margin that we spoke about there. The margin is the margin between the plane margin. Rho is the margin, d is the diameter of the smallest sphere that can enclose all the training samples, and MO is the dimensionality. So, he said that it is bounded by that, okay, and the dimensions. Intuitively, this implies that regardless of the dimensionality M0, we can minimize the VC dimension, that is the dimension H, by maximizing the rho, that is the margin. Thus, complexity of the classifier is kept small regardless of the dimensionality. Just let us discuss this a little more. What we have done up to now is, we are saying that instead of having just one line separating the two data points, we are increasing it such that there is a margin separating, there is a width separating the two data points. And of course, the other advantage of support vector machine is we consider only the support vectors as important, that is there. Now, we are trying to find a justification for the maximum margins. Why should we use maximum margins? So, for that what he is saying is, the optimal, always we are trying to find the optimal linear plane separator. It will have a dimension H which is bounded by this, H is less than or equal to minimum of the dimension divided by the rho and M0. M0 is the dimensionality of the data space. I mean, D is not the dimensionality, D is the diameter of the smallest sphere that encloses all the training points. Now, the idea is that whatever may be the dimension, okay, regardless of the dimension, we can minimize the VC dimension H by maximizing the value of the margin. So, this means that irrespective of the margin, the complexity of the classifier remains the same. So, that is what Wapnick and Chervonikis said, and one of the reasons why support vector machine has become very popular. Now, let us look at the summary of linear SVMs. The classifier is a separating hyperplane, yeah, and so that is the classifier. The most important training points are support vectors which define this hyperplane, because the support vector decides on what is the hyperplane, and quadratic optimization algorithms can identify training points with a non-zero Lagrangian multiplier alpha. So, here this is the optimization, and both in the, so what are you doing here? We are not actually, the optimization problem is not actually finding the plane or the margin for you, it is finding those data points that will maximize that optimization with, it will maximize which are the data points you want to find, identify the data points. Both the dual formulation of the problem and the solution training points appear only inside the inner products. Now, let us go into non-linear SVMs. Now, what we did there was, we did three things. One, we assumed that it is a linear, then we said that there may be some noisy data, so we had to introduce slack variables, and we went in for what was called a soft margin rather than a. Now, we go to the next part, which is called as data sets that are linearly separable with some noise, okay. So, here you have this is if it is separated like this, the blue comes on the other side. So, this is some noise, but that we tackled using slack variables. But what are we going to do if the data set is just too hard to tackle, that is, it is not just some noise. So, if you look at the next example, you will see that, the next example, you will see that red comes in the middle, blue comes, red comes on this side. So, this is not noise, you have quite a lot of data points coming this way. So, how about mapping data? So, how do you solve this? This is called a non-linear SVM. If you visualize it, you will have, you cannot separate it like this, you will have here one, here one, here one. So, it is not linearly separable. The separating plane is no more longer linear. So, how does SVM tackle this? SVM we said is binary and it is linear. So, what we do is we take this data that we have and we map it to a high dimensional space such that you can linearly separate it. So, if you take here, this is the point, and you can see that you have if you map it to a higher dimensional space, you may be able to linearly make it separate, I mean make the data linearly separable. So, the general idea here is nonlinear SVMs, they are the feature spaces. This feature space itself is made into converted into a higher dimensional space. So, general idea, the original feature space can always be mapped to some higher dimensional space where the training set is separatable linearly. If you look at the example given here, you have a 2-dimensional data set and which is not linearly separable. If you see that circle there, that is the separation margin. It is not linear, it is in the form of a circle. Now, if you are able to map this 2-dimensional into a 3-dimensional problem, you can see that you have a hyperplane that you can use to separate out the data points, the red and the blue. Now, the question is, what is the function you use to convert this 2-dimensional into the 3-dimensional? That is the crux of the problem. Okay. So, we want to map this 2-dimensional to 3-dimensional. This is the concept of how the feature space is mapped to from a lower dimension to a high dimensional space. This comes in lot of places. This function is the so-called kernel function. Okay. So, this is typically necessary for points. We take the similar example. You see here, this is a hard margin. So, we require all data points to be classified correctly and there is no training error. So, this is the training set is noisy, it is noisy also. The solution is you have to use very powerful kernels. So, this particular example is the case of overfitting. Okay. If you do noise and do this, it will become very overfitting. So, you should not do that. So, the idea is to use the kernel trick. So, again I will repeat, the previous example we said that if we have, previously we said that if you have data points and you have noise, you can use the slack variable. But if you use the slack variable and try to do overfitting, increase the increase the contribution of the slack variable, it becomes overfitting. So, instead of doing that, we take this data space, we do not consider it as noise, but we convert it from a lower dimension to a higher dimension and then use the kernel trick. So, what is the kernel trick? The linear classifier relies on inner product between the vectors. So, this is it. So, every data point is mapped to a higher dimensional space like this. So, x becomes psi of xi. And so, instead of this inner product now being xi t xj, we have phi xi to the power of t x to the phi xj. So, this is the mapping of the original dimension to a high dimension, and that phi there is the kernel function. A kernel function is a function that is equivalent to the inner product of the feature space. That is the function that we have to find out, and that is the, we are not going to detail mathematically of how to find out that function, but that is the concept that we use. So, example, you have a 2-dimensional x1 x2, we want to convert it, this is represented like k of x1 xi xj like this, and now we convert it as like this, okay, and now phi I xi of t, phi xij, and phi of x is this kernel function which we use. So, we want to convert the 2-dimensional space vector into a 3-dimensional vector. Thus, a kernel function implicitly maps to a higher dimensional space. So, what are the functions that can be kernels? Some functions checking out can be very cumbersome, it is not easy to find the kernel. So, we use Mercer's theorem. Every semi-positive definite symmetric function is a kernel. So, semi-positive definite symmetric functions correspond to semi-positive definite symmetric gram matrix which is given here. So, you have a method of finding out this particular kernel function. We are not going to go into the details of that, but just to tell you. Examples are linear mapping of phi x goes to phi of x, where phi of x is x itself. Polynomial of power, you can go that way, or you can go for Gaussian, which is the radial basis function. So, mapping of x to phi of x, where phi of x is infinite dimensional, every point is mapped to a function which is a Gaussian. So, that is an infinite dimensional. Polynomial is the next one. So, you have linear, you have polynomial and you have Gaussian. So, high dimensional space still has intrinsic dimensionality d, but linear separator corresponds to non-linear separators in the original space. So, whatever you get here the linear separator, it corresponds to the nonlinear separator that you would have got in the original lower space. Okay. So, nonlinear SVMs mathematically, again you have the dual formation problem, except that here you have additionally the kernel function, the solution is the function of x, the same thing that we saw for linear, except that here additionally instead of xi and xa being put directly, we have a higher dimensional one. The optimization technique for find the Lagrange multipliers remain the same. So, some of the application we will just touch upon this, we will go into detail in the module 2. So, SVMs are currently among the best performers for a number of classification tasks ranging from text to genomic data. SVMs can be applied to complex data type beyond feature vectors, example graphs, sequences, relational data by designing kernel function. So, kernel function is the major thing there. Designing that is not a trivial problem, again to tell you. SVM techniques have been extended to a number of tasks such as regression, principal component analysis, etc., where the dimensionality can be directly mapped. And most popular optimization techniques for SVM use decomposition to hill climb over a subset of the Lagrange multipliers at a time. And tuning SVMs remain a black art. Selecting a specific kernel and parameters is usually done in a try and see manner. You have no proof to say this is the best kernel and these are the best parameters. It is still a try and see, it is that. So, what we have done here is we have explained the maximum margin classification, we have described linear and nonlinear SVMs, we have discussed about the optimization problem, we have touched upon what is kernel functions, though we did not take an example and explain how a kernel function is selected. Again, it is a try and do, and we have just listed some SVM applications. So, with that we will wind up the first module on support vector machines. Thank you.